In this video, we'll take a look at section 7.2, something called the unit circle, and the sine and cosine functions around the unit circle. So before we do that, we're going to review a couple of triangle relationships that you learned in geometry. The first one is the relationship between sides and what we call special right triangles. The first triangle is a 30, 60, 90 right triangle, and the relationship of the sides, if the hypotenuse is h, then the shorter side is 1/2 times h, and the longer side is square root of 3/2 times h. What we're going to look at in a unit circle is we're going to take a look at triangles inside the unit circle that have a radius of 1. So if h is 1, then the short side would be 1/2, and the longer side would be the square root of 3/2 in the 30, 60, 90. The other special right triangle is called a 45, 45, 90 triangle, where two sides are the same length. And if the two sides are the same length k, then the hypotenuse is the square root of 2 times k. If the hypotenuse is 1, then finding the lengths of the two sides, you would divide by the square root of 2. So either side would be 1 divided by the square root of 2. Now it's a rational, we need to rationalize the denominator. So 1 over the square root of 2 multiplied by the square root of 2 over the square root of 2, and we get the square root of 2 over 2. So in a 45, 45, 90 triangle, if the hypotenuse is 1, then the two sides have length square root of 2 over 2. So that's the first idea. The second idea has to do with right triangles as well. They're trigonometric ratios. So in a right triangle, this triangle ABC, the three sides, the three angles are denoted by capital letters, angle A, angle B, angle C. And then if we look at angle A as our angle of reference, okay, the sides, the small case letters, so opposite capital angle A is small case A, side A. And in relation to that angle A, it's the opposite side. B is opposite side B, C is opposite side C. So the way that we name the sides in relation to angle A, little side A is opposite, side B is adjacent, and side C is the hypotenuse. There are 6 different trigonometric ratios in the triangle. In this section, we're concerned with 2 of them, and then we'll do the other trig functions in a later lesson. So the sine of an angle, the first trig ratio, is the ratio of the opposite to the hypotenuse. So in this case, opposite would be A, hypotenuse would be C. The cosine of an angle is the ratio of the adjacent side to the hypotenuse. So in this picture, that would be B over C. So we're going to take these ideas of special right triangles, and by the way, the relationship between these sides we get from Pythagorean theorem. So just a reminder, the Pythagorean theorem, a squared plus b squared equals c squared. That's how we get these values in the special right triangles. What we're going to do is take these special right triangles and put them on a circle on the coordinate plane. So a unit circle has a center 0, 0, and a radius 1. So I'll draw that unit circle here. So this is on the xy axis. The center of the circle is 0, 0, and it has a radius equal to 1. So there's a nice, if you pick any point on that circle, so let's take a look at just the first quadrant. If you pick any point on that circle with radius 1, we can drop down a vertical, horizontal with the x-axis and create an angle, and that creates a right triangle. Our angle is angle T. So let's see, in a unit circle, the length of the intercepted arc is equal to the radian measure of the central angle. Let xy be the endpoint on the unit circle of an arc of length s. The coordinates xy can be described as functions of the angle. So if you take a look and think about this as a right triangle, on angle T, the sine of angle T is the opposite side over the hypotenuse. So the opposite side in the unit circle is going to be the sine. Then the cosine is adjacent over hypotenuse, so it's cosine t over 1. So that means any coordinate xy on the unit circle, the x-coordinate is the cosine of the angle, the y-coordinate is the sine of the angle in standard position. So if we think about calculating sines and cosines, the first is maybe the easiest coordinates to find are the ones that are along on the quadrantal angles. So at 0 or 360 degrees, the coordinates 1, 0. The coordinates at 90 degrees, or pi over 2, the coordinate is 0, 1. The coordinate of pi, or 180 degrees, is negative 1, 0. And the coordinate at 3 pi over 2, or 270 degrees, is 0, negative 1. So if you want to find the sine or cosine of the quadrantal angles, it's the x-coordinate and the y-coordinate. So if we want to calculate the cosine of 90 degrees, the cosine of 90 degrees is the x-coordinate. So the x-coordinate cosine of 90 is 0. And then the sine of 90 degrees, or pi over 2, is the y-coordinate. The y-coordinate pi over 2 on the unit circle is equal to 1. So every point around the unit circle, xy, is the cosine of the angle in standard position for the x-coordinate, and y equals the sine. So what we want to do is we want to find as many exact values as possible by taking the angles of our special right triangles inside the unit circle. So in the first quadrant, if you take a look at, let me put in red here, the first triangle right here, if this is an angle of 30 degrees, then the angle up top is 60 degrees, and this is a 30, 60, 90 triangle situated inside the unit circle. If the hypotenuse of that triangle is 1, then the sine of the angle, which is opposite over hypotenuse, is equal to 1/2, and the cosine, which is adjacent over hypotenuse, is equal to the square root of 3 over 2. So the coordinates at pi over 6, or 30 degrees, is the cosine of 30 degrees and the sine of 30 degrees. So that means the cosine of 30 degrees is equal to square root of 3 over 2. The sine of 30 degrees is equal to 1/2. And similarly, if you want to use radian measure, cosine of pi over 6 is square root of 3 over 2. The sine of pi over 6 is 1/2. So if you take the 30, 60, 90 triangle and orient it so that we have 60-degree angle, then what you end up with is a longer side length of square root of 3 over 2 and shorter side length 1/2. So the cosine of 60 degrees is 1/2. The sine of 60 degrees is square root of 3 over 2. Then the other right triangle, special right triangle, that we could embed inside the unit circle is the 45, 45, 90. So if we have 45 degrees, the coordinate on the unit circle for 45 degrees, or pi over 4, are the two side lengths of your triangle, square root of 2 over 2 and square root of 2 over 2. That means the cosine of 45 degrees is the square root of 2 over 2, and the sine of 45 degrees is the square root of 2 over 2. So the idea of putting special right triangles is to try to find as many exact values as possible for the ratios of certain angles. So we can find exact values for 0 or 360, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Okay? And exact values mean that they're in terms of radical. They're not to the decimal places. Okay? If you were to use the calculator to find the sine or cosine of 45 degrees, let me make sure my mode is in degrees. If you use the calculator, the sine of 45 degrees, you end up with the decimal equivalent, 0.707106. So if you use the calculator, you're always getting an approximation and you have to round. So what we'd like to be able to do is use the exact value so you don't have to round. The cosine of 45 is exactly the square root of 2 over 2. The sine of 45 is exactly the square root of 2 over 2. The decimal approximation is about 0.7071. So when your homework asks for exact values, leave it in terms of square root. If it asks you to round, use the calculator. All right, so in the first quadrant, those are the exact values that we can find for angles. So how would we use reference angles in symmetry to find cosine and sine, or exact values, of the angles all the way around the unit circle? So for example, if we take a look at 120 degrees, remember that the reference angle for 120 degrees is actually the angle it makes with the x-axis. So the reference angle is 60 degrees. Well, we know the cosine and sine of 60 degrees is the coordinate 1/2 square root of 3 over 2. So if we use the reference angle, notice we have a negative value for x. Then this point, if you think about it using symmetry, it's a reflection over the y-axis. The coordinates of that point are going to be negative 1/2 square root of 3 over 2. So the cosine of 120 degrees is negative 1/2. The sine of 120 degrees is square root of 3 over 2. And we can think of it the same way with reference angles or with symmetry. 135 degrees has a reference angle of 45, or you can think about it as reflecting the point xy across the y-axis. This coordinate would be negative square root of 2 over 2, square root of 2 over 2. So that tells us the cosine and the sine of 135. Same way with 30 degrees. The reference angle for 150 is 30 degrees. So the coordinates of this point would be negative square root of 3 over 2, 1/2. So if you're in the first quadrant, the cosine of your angle is positive. The sine of your angle is positive. In the second quadrant, the cosine of the angle is negative, and the sine of the angle is positive. So we can take the same idea of symmetry and the same idea of reference angles and find out the exact values for sine and cosine all the way around the unit circle. So at 7 pi over 6 or 210 degrees, the reference angle would be 30 degrees. Then we know the sine and cosine of 30 degrees are the coordinate square root of 3 over 2, 1/2. But if we're in the third quadrant, think about it as reflecting the point, then they're both negative. Negative square root of 3 over 2, negative 1/2. Then at 5 pi over 4 or 225 degrees, we get negative square root of 2 over 2, negative square root of 2 over 2. 240 degrees has a reference angle of 60. So we're going to end up with negative 1/2, negative square root of 3 over 2. So notice in the third quadrant, cosine is negative and sine is negative. Then in the fourth quadrant, if we follow along our reference angle idea or symmetry, 330 degrees has a reference angle of 30. So if we reflect the point across the y-axis or the x-axis, we get square root of 3 over 2, negative 1/2. Reflect. 315 degrees has negative, positive square root of 2 over 2, negative square root of 2 over 2. And 300 degrees, or 5 pi over 3, has a coordinate 1/2, negative square root of 3 over 2. So in the fourth quadrant, the cosine is positive, the sine is negative. Okay? So these are all of the exact values, including your quadrantal angles, on the unit circle. So in your canvas, you've got a printout of the unit circle. You've got exact values of the trig functions all the way around the unit circle. So you can use this as a reference, and we're going to use this for the next couple of sections as well. Okay, so keep this handy, print it out, and then just kind of understand where all of these exact values come from, is they're really putting special right triangles in the first quadrant and then using symmetry and reference angles to create the rest. All right, so that's the main idea in this section. One other idea and an identity that I want to talk about is something called the Pythagorean identity. So remember that Pythagorean theorem is in a right triangle, a squared plus b squared is equal to c squared. So when you have a triangle embedded inside the unit circle, remember the coordinates of that triangle are the cosine and the sine of the angle. And those are also the side lengths. So if you take the cosine squared plus the sine squared, which are the lengths of your triangle, that equals 1. So what do we use the Pythagorean identity for? Well, if you have the cosine or sine of an angle, you can always find the other trig ratio. So example, if our cosine is equal to 24 over 25, and we know t is in the fourth quadrant, find the sine of t. Well, we put this in our identity. Identity is just a formula. 24 over 25 squared plus the sine squared is equal to 1. Then square your 24 over 25. So we're going to take 24 and square it. We get 576. 25 and square it. 625. We get 576 over 625. Plus the sine squared is equal to 1. Subtract 576 over 625 from each side. We end up with the sine squared is equal to 1 is 625 over 625. So I'm going to take 625 minus 576. And we end up with 49 over 625. The last step, square root both sides. Whenever you square root both sides, the sign is a plus or a minus 7 over 25. So how do we know if the sign is positive or negative? It tells us t is in the fourth quadrant. So in the fourth quadrant, the x values, cosine, is positive, and the y value, sine, is negative. So our answer is the sine of t is equal to negative 725 because it's in the fourth quadrant and the sign is negative. All right, last example. If you have the sine is equal to the square root of 33 over 7, and you know your angle is in the second quadrant, find the exact value of the cosine. So we take our same identity, cosine squared theta plus the sine, square root of 33 over 7, squared is equal to 1. We get cosine squared plus 33 over 49 equals 1. Subtract 33 over 49 from each side. One is the same thing as 49 over 49. The cosine squared is equal to, let's see, 49 minus 33 is 6, 16 over 49. Square root both sides. The cosine of our angle is equal to plus or minus 4 over 7. And then to decide which, we have to see which quadrant we're in. So if we're in the second quadrant, we don't even need to know exactly what the angle is. We just need to know that in the second quadrant, the cosine is negative, the sine is positive, so the cosine is going to equal negative 4/7 because it's in the second quadrant.